Welcome, guys. So in this video, let's talk about a little bit the quantum so-called hidden subgroup problem. Okay, so just a short video summarize that a little bit generalized to the Shor's algorithm. So please subscribe to my channel. So the case one is that so let's maybe talk about the hidden subgroup problem. Then talk about okay. So the idea is that if somebody give you a group G, then there's a color. Okay, so map to a color. So you carry color is not important, right? You just map it as a finite set. So we say that f heights to G means that there's a subgroup H. F of x equal to f of y if x y belong to some coset of H. So everybody knows about group theory. So if you have a normal you have a subgroup, then that subgroup will separate G into different cosets, and for each coset, the number of elements are the same. So we restricted our G to be we restrict G is not need to be finite, right? But okay, so the f x h will equal to f of x. Then this is called H periodic. Okay, so if you think carefully, this definition generalizes our original period finding if we assume that the G is integer and H is just some multiple of that integer. And so that means Shor's algorithm can solve this problem when G is positive. G is an integer. Okay. So the task is to find H, right? So the idea is that we can use quantum mechanics. You can use quantum computer. So we start from all the combination of the possible combination of G, and then we take the quantum Fourier we take the Curie, and we get x f of x, right? Then we measure the second register, then we will get some coset representative. So basically, we will pick some coset. So the result will just like this. We will pick some coset, and we collect how many all the elements in that coset. So finally, is that we need to perform some magically operations, which we can gain some information of this H. But the problem is that in general, there's no efficiency quantum algorithm for general group. Okay, but we indeed have some some partial results. So the famous result is that Shor's algorithm tell you that if G is commutative, basically, or you want to say that G is an abelian group, then the answer is yes. There's a exponential speed up. So for the abelian group, that G is just the direct sum of the cyclic. Okay, so this is the college level algebra. If you don't know this, you can go to my channel and type something. Maybe you can find the proof. Okay, the case 2 is that G is not abelian. G is a non-abelian group. Then the answer is we don't know. So up to now, the answer is no. So the hidden subgroup problem for the first one is that let's say it's called Simon's algorithm, right? Basically, you got your total group is 0 to bit string, right? And in the multiplicative, well forms a group, and so basically your H is H2n, right? So okay, so by the way, I didn't write H here, so or you can view this as a finite group to power n, but plus as the group. So for the Shor's algorithm, it's this one, the integer and with plus, and this guy is that zn with plus. Basically, and also this is called Shor's discrete log problem, and I may talk about this. So zn cross zn by plus. Okay, and this is famous called Pell's equation, x squared minus dy squared equal to 1. And this is very famous. This is algebraic problem. Then the G is the real number, and the group operation is plus. Okay. Also, the two famous are that if you consider your general group is the dihedral group, so this is a non-abelian group. Then this can be doing the approximate shortest vector problem in the lattice. Also, probably the famous one is that since there's a Kelly theorem, means that any subgroup, so any group can be viewed as a subgroup of a symmetric group. with a permutation with n letters. So if we consider group G is Sn, which is a symmetric group, permutation of n letters, then this will corresponding to the graph isomorphism. Okay, so and the graph isomorphism is really people think graph isomorphism is not NP complete, but it's already really difficult. So graph isomorphism is very close to the general NP complete. Okay, but up to now we don't have the good quantum quantum algorithm for solving this dihedral group and the symmetric group. Actually, for any non-abelian group, we don't have the good results. Okay, so let's just my short page, my own notes of the hidden subgroup problem. So summarize some basic hidden subgroup and tell some up to now tell some reasons, or basically tells the stage. Okay, so that's for today. And the next time we may starting to talk about the discrete algorithm and the Pell's equation or other interesting quantum algorithms. So be sure to subscribe to my channel. Thanks.